Hey, welcome to Ones and Zeros. My name's Ben, and today we are doing another episode of our Discovering STM32 series. This will be episode number 12, following on from episode 11, where we had a look at getting the driver written for the touch controller for the LCD screen. And in this episode, we're going to be looking at getting the driver written to be able to set up the QuadSPI peripheral. And that will then give us access to the MX25L512 chip. That is a 64 megabyte flash memory chip that's on the Discovery board that we can use for being able to store data. We'll also be looking at integrating that in a future episode with the FATFS middleware so that we can actually format it with the FAT file system, for example. But we're going to write the driver so that it's not only good for being able to do that when we go to have a look at that, but so that it's got a couple of other different sort of modes and ways of accessing it that can be potentially useful in other certain circumstances, which we'll have a look at as we get to that as well. So using, of course, our Discovery, our STM32 F769I Discovery board, that we've used in this episode, this series so far, and slowly building upon that to get a fully working system with all of the features. So coming up after this episode, we're going to be looking at getting the drivers written for the SD card. We'll have an episode coming up where we look at integrating FATFS, as I mentioned, so that we can use the FAT file system not only for the flash memory, but for the SD card as well, which allows us to more easily transfer files from, say, a PC. I'll also, in future episodes, be looking at getting the audio side of things up and running, so getting a driver written for the audio codec and the SAI peripherals so that we can stream audio into and out of the STM32. Looking at ways of generating various sounds and things like that, potentially playing back sounds from files on the SD card, stuff like that as well. And a bunch of other stuff beyond that as well, but that's kind of the short-term goals that we've got at this point. But like I said, today going to be looking at getting the QuadSPI peripheral and the flash chip set up and working, and getting that driver written. So let's dive into some code. So we've got the code as it was at the end of our touch driver video. I have just deleted a little bit of the code in the processing loop from where we were outputting some of the stuff from testing the touch controller. But aside from that, it's basically as it was at that point and ready for us to go through and get a touch driver written and tested in this episode. Also just like to say a quick thank you to all of the people that have been liking and leaving comments on the videos. That's really awesome. All of the new subscribers definitely inspires me to want to keep developing videos. And of course to our two awesome patrons that we have so far, which is Craig and Luther, which we have up there. So both of those guys. So that is really awesome to see that people are liking the channel, enjoying the content and things like that. Definitely enjoy doing it. So glad other people enjoy watching it. So onto our flash driver. So first thing we're going to want to do is have a look at figuring out which pins are actually connecting our STM32 chip via our QuadSPI peripheral over to our flash memory chip. And there's going to be 6 particular signals that we're going to have there. So to go along with where we've done our pin definitions in our setup.hpp file for our user LEDs and our UART and our LCD backlight and reset pins, we're going to put in some definitions here for the 6 pins that we're going to need for the QuadSPI peripheral, which are these guys here, as per the documentation for this Discovery board. Well, notice, whereas with a normal SPI peripheral, you've have your chip select and clock pins, and then you'd have a MOSI or master out slave in and a master in slave out pins, so those 4 for a typical SPI device. QuadSPI is a little bit different in that it still has its chip select and its clock, but rather than having our MOSI and MISO, it actually just has 4 data pins, which the peripheral can go through and set those as inputs or outputs, things like that, as needed to either transfer data to whatever's connected to it or receive data from whatever's connected to it. And we'll sort of see as we go through and set up the driver how it makes that work. But that's the reason why it's called QuadSPI, because it has 4 data channels effectively, so that it's actually able to send data in parallel, and as a result can actually get more performance out of it than you would typically get out of a standard SPI or SPI bus. So that's our pins. So our chip selects on pin B6, our clocks on B2, and then our data pins are C9, C10, E2, and D13 respectively. So we've got those definitions there, so that they're good to go for us. We're going to need to create a couple of files for our driver. So firstly, a header file, which we are going to call QAD QuadSPI, and a source file, which will be also QAD QuadSPI.cpp. Now we will go through and let's just use this one. This will do. Go through and copy a header from one of our previous files just so that we can use that. Pop that in here. And this will be our QuadSPI flash driver. We might even just put in that it's the MX25L512 flash chip that it's going to be looking after. Just fix up our file name and the date, which is the 22nd January 2022. Like so. Fix up our prevent recursive inclusions. And pop one down here as well. Alright, that's that one. Grab hold of all of that. Jump over to our source file. Pop that in there. Get rid of that one. Change this over to QAD QuadSPI.hpp. And we'll get rid of that one as well. And our source file is good to go to have some code chucked in it. Alright. So, couple of things that we're going to need. So a couple of enums to allow us to track a couple of different things about our driver. So we'll get those in there first up. So we're going to want one which will be a status enum, so that we can retrieve the particular status of the flash chip, whether it's ready to go, whether it's busy doing something, or whether an error has occurred. And then we're going to have an enum to let us know what particular mode it is in as well. So with the QuadSPI peripheral, there's a couple of different ways to be able to access it. So we can access it just by reading or writing data. We're going to have some methods to be able to erase certain aspects of the chip as well, or read to or write to the chip. But there's also a thing called memory mapped mode as well. Now, what that allows us to do is almost access that flash as if it's just a device on the STM32's bus with its own memory space, similar to what you would have seen when we went through and did the video looking at the FMC and SD RAM. where the SDRAM is basically just accessed by reading or writing to a specific address, and that's just handled by the FMC peripheral. We can do something similar with the QuadSPI and the flash memory, where we can set it up in such a way so that we can access it just as a device on the bus with its own address space. However, unlike the SDRAM, when we do that with the QuadSPI, we're only able to read from it. We can't write to it, so it effectively acts as a ROM in that situation. So if we want to be able to write to it or erase it, we're going to want to have it in normal mode. But we want the option to be able to switch it into memory mapped if we want to be able to use that. Where that could be handy is, say, if you're writing, say, a game that is running off the Discovery board, and you have your game resources on the flash chip. So things like graphics that you might be drawing to the LCD, or sounds that you might want to be streaming via the audio codec, things like that. Then setting it up as memory mapped will potentially allow you to do that in a slightly easier way. And in that situation, chances are you're not going to be needing to overwrite those while the game is running. You're only going to be wanting to read them. So that's where having it in memory mapped mode may be something that's handy to do. So we're going to build that into the driver anyway, because there is certain situations where I like to be able to use it. But you have the option, so you can switch it into memory mapped and out of memory mapped as needed. And if you want to use memory mapped, but you want to be able to write data to the flash memory occasionally, you can just pop it out of memory mapped mode, erase the sections of the chip you need to write the data to them, and then pop it back into memory mapped mode. So that's an option as well. Say in the situation with the game where you want to be able to save, have save files for the game stored on flash, which is, you're not going to be saving it all the time, so you can pop it out of memory mapped mode to be able to save a file and then jump back in memory mapped mode to continue running the game. So that's what that's all about, and we'll have a bit more of a look at that as we go through and get that stuff set up as well. The actual driver class itself, we're just going to call Q8E QuadSPI. And let's create the driver class for that one. I have a private section where we can store some of the driver data, and a public section. And we're going to have another private section as well. So as we've done with a few of the drivers over the course of this series, because there's only one QuadSPI peripheral that we're using on this particular chip, we're going to set this driver up as a singleton class so that only one copy of the class can exist, because we don't want multiple copies being created where they could interfere with one another. So you may recognize that from previous videos, such as when we did the FMC and SDRAM video. Now, we're going to want a private enum in here to assist us in situations where we may need to deinitialize the peripheral and the flash memory, which, again, if you've watched previous videos, you might recognize that, but we'll explain what that's for moving forward. We're going to want some flash constants just to track various things about the actual flash memory chip, the MX25L512 chip that we're using. So firstly, we're going to have one to hold the overall size of the flash memory, which will be, make sure I get the right amount of zeros in here. So 400000 in hex, which is 64 megabytes. Now the flash memory is also broken up into sectors, subsectors, and pages. which are all varying sizes. So the sector size for this one is 10000 in hex, which I should be able to convert in my head, but can't right now. So let's just cheat and use our handy Windows programmer calculator, which gives us 64 kilobytes. We have our subsectors, which are 4 kilobytes. And we have our pages, which I'm guessing is going to be 256 bytes. Exactly. So that one I can do in my head a little bit easier. All right. So also going to store a couple of other things in here, which is how many sectors we actually have on the chip, which we have 1024 of those, and 1024 sectors at 64 kilobytes each is 64 megabytes. We have our subsectors. Really doing good with the typing this evening. So we have 16,384 of those guys. And our pages, we have 262,144 of those. Now, the other thing we're going to store in here is the base address in the address space for when we are operating in memory mapped mode, which is 9 followed by 7 zeros in hex. So if we're in memory mapped mode, then we can read from that particular address up to 93FFFFF. So let's make a note of that. That will be to 93, 1, 2, 3, 4, 5, 6. So that's the range of addresses that we can read from in memory mapped mode in order to read from the flash memory. Now we're going to have some driver data as well. So firstly, you're going to want to track what state we're currently in, which will be a QA init state enum, which is defined in setup.hpp. And then we're also going to have our QAD QuadSPI memory mapped enum that we've defined near the top of this header file, so that we can track whether we are actually in memory mapped mode. And finally, we're going to need a handle to our QuadSPI peripheral so that we can use the HAL methods to be able to access that as well, which we're just going to call MS handle. So not too much more that we're going to need as far as storing data in the driver. We're going to have a private constructor because of the fact that we're going with a singleton class. So we don't want the constructor being accessed by outside of the class. And we're going to want to set ME init state to not initialized when the class is created. Make sure we spell that correctly. And set our memory mapped state to memory mapped disabled. Like so. Now, because we're going with a singleton class, we're going to want to delete our copy constructor and our assignment operator so that we can't accidentally make copies of the class. So just going through and deleting the copy constructor and deleting the assignment operator there. And in order to get a pointer to the class and make sure that the class being created is all handled, we're going to need a get method for that one, which returns a reference to the Q8E QuadSPI driver. So just setting up a static instance of that class there. So by creating a static variable for that, it's going to get access to the only copy of that class that's capable of existing. If we haven't accessed that previously, so if the get method hasn't been called previously, then the first time we call it, it will automatically go through and call our private constructor in order to make sure that that's set up the way we need it to there. And then this one just goes through and returns a reference to that class so that we can access it as needed. So we're going to want a bunch of different methods to give us access to this one. So let's just go through and pop all of those guys in there in one go. And let's have a look at what we've got. So we've got our initialization and deinitialization method, and you'll notice all of these public methods are static so that they can be accessed as part of the singleton class, and they then go through and call their respective implementation methods. So we're going to have a bunch of private methods which will basically have the same name as each of these, just with IMP underscore in front of them to let us know that those are the actual implementation methods. That's where the actual code lives. And these static methods are basically just there to allow us to access those from outside of the singleton class. So we'll notice that for each of these, it will go through and obtain a handle to the singleton class or a reference to the singleton class, and then go through and actually call the relevant implementation method. I will have a video coming up in our C++ series looking at singleton classes, hopefully in the next couple of weeks, so that if that's a little bit confusing, it'll make a little bit more sense. But again, if you've seen us working with singleton classes in previous videos, you probably find that a little bit familiar. We've got the methods related to actually accessing our memory mapped mode, including a method to allow us to enter memory mapped mode, to exit memory mapped mode, to find out whether we are actually in memory mapped mode or not, as well as to retrieve the base address as well, so that we know sort of what address we can start accessing the flash memory from. We've got a few methods to allow us to get access to the size of the flash memory, to the size of the sectors and the subsectors, as well as to find out how many sectors and subsectors are there. And we'll notice that these are just basically returning the value that's stored in the constants that we defined in the private section of the class a little earlier. We'll have some data methods to allow us to just do a read of the flash memory. So we supply it with the address we want to read from, a pointer where it can actually store the data it's reading, as well as how many bytes we want to be reading from the flash memory. We've got methods to just be able to read a specific subsector or a sector, so it'll read the whole subsector or sector. In that case, we provide an index of which sector or subsector we want to read from, as well as a pointer where it can actually store that data. Similar thing to our write method. Now, because the flash memory, the way it works is if we go to write something, it needs to be erased first before we can actually write data to it. So with this write method, we can supply an address and a pointer to the data we want to write, as well as how many bytes. But if we try to use this one to write to an area that hasn't been erased yet and already has data in it, it's not going to write correctly. So in order to use that particular method, you need to be aware of that and be erasing whichever bit of memory that you want to write to first. We've got these two methods which allow us to do an erase and write on either a subsector or a sector, so it's taking care of the erase for us, and in this case it will write an entire subsector or an entire sector. So subsector being a 4K block and a sector being a 64 kilobyte block respectively. And then we've also got some methods to allow us to do erases on various parts of the chip. So we can do an erase on a sector or a subsector, supplying the particular address at the location that we want to erase. We've also got methods to allow us to specify the index of the sector or subsector as opposed to providing an address. So just allows us a couple of different approaches as to how we go about doing the erase, depending on, do we want to supply the index or do we want to supply an address? And then we've got a method to allow us to erase the entire chip in one go if we want the whole thing cleared. And finally, we're going to have a method to allow us to retrieve the current status of the flash chip as well, based on the particular enum that we created up here, so that we can find out, is the flash memory currently ready to go? Is it currently busy doing something? Is it currently writing data or something like that? Or is there an error that has occurred? So that's a bit of an overview of the particular methods that we've got there. So kind of grouping those into our initialization methods, methods for working with memory mapped mode, stuff related to retrieving sizes and things like that, stuff to do our reads, our writes, and our erases, as well as our status method. So there's a few there, but they are all fairly simple. And then we're going to have our private implementation methods, which is where the actual code will be getting put in. Now, for each of our static methods, we've got an associated implementation method. We do also have these guys, which don't have associated static methods. These are the ones that are responsible for actually setting up our GPIOs, initializing the peripherals, things like that. And these will be called from our imp init and imp dinit respectively as needed. The reason for that I'll kind of explain a little bit as we go to pop the code in for those particular methods. We've got our stuff for memory mapped mode, our ones to do our reads, writes, erases, and get our status. And then we've got a bunch of tool methods as well, which aren't used by anything outside of the driver class. They're basically just allowing certain things inside the driver class to more easily manipulate what mode and things the flash memory is in order to initialize it, or to do things like putting it into write enable mode so that we can actually write to it, check if it's ready to do something. So if it's busy, if we need to be able to write data to it, but we don't want to try and do that while the chip is busy doing a previous write, for example, then we've got methods there to be able to allow us to do that as well. So I'll explain each of those as we go through and put the code in for them as well. So that's basically all of the methods that we're going to need to put into the class here. The rest of the stuff's going to be going into our source file. So let's jump over to that one. We'll save that first. Jump over here. And let's get some code put in here. Now, with our MX25L512 chip, there's some certain definitions that we're going to want to put into the source file, which are going to be used by the various methods, which are all of these ones. So all of these guys are the definitions for the various commands that we're going to be using. So when we go to access the flash memory, we're going to send it a command to let it know what do we want to do. Do we want to do something like read its status register? Do we want to write memory to it? Do we want to tell it that we need it in write enable mode so we can write to it? Do we want to do an erase? Things like that. So these are the particular bytes for the commands that we're going to be using. So by putting the definitions in there, it kind of allows us to have the code make a little bit more sense, because we can actually use the define rather than just having random numbers in there that may not make sense. All of these are available in the Maxim MX25L512 datasheet for the chip itself. There is more, but these are just the ones that we're going to be using for this particular driver. We've got some defines for various bits in the status register. So we can check whether a write is currently in progress. If it is, then the first bit in the status register will be set. If write mode is currently enabled, the second bit will be set. We've also got a bit which allows us to check whether QuadIO mode is enabled. So with QuadSPI, it's not necessarily using all 4 data lines in one go. There is various modes where it may only be using one. So when we first initialize the chip, it's going to be in single IO mode, and because we want to make use of all 4 data lines to get data moving quicker, we will need to go through and actually put it in QuadIO mode, so that'll be part of our setup stuff. And then there's also a control register in the flash chip as well. So we've got some various defines here to help us do things like selecting the output driver strength for the data lines, as well as things like doing protecting of various blocks, what addressing mode we're in, because you can put it in 3-byte or 4-byte addressing mode. We'll typically be using 4-byte addressing mode, and how many dummy clock cycles it requires during various operations as well. And then just some configuration definitions here. So how many dummy cycles are being needed in particular situations, as well as how long it takes typically to do a full chip erase, to erase a single sector and erase a subsector. So these 3 here are used as timeout values effectively when we go to do those various operations, which we'll see when we have a look at the code for those as well. So first things first, we'll get an init and dinit methods popped in here, which are these guys. So our init method is basically just going through and checking if we are currently initialized. So if we're already initialized, there's no point initializing again, and we can assume that because we're already initialized that everything's okay. So we can just return QA okay in that situation. If we're not initialized, then we're going to call the perif init method to go through and actually initialize the peripheral. And if that fails, we'll return QA fail. If it succeeds, then we'll set our init state to initialized and our memory map state to memory map disabled, because when we first initialize, we're not going to be in memory map mode. That's going to be an extra step if we want to be using that. And then we can just return QA OK in that situation to say that that has initialized correctly. Now we've got our dinit method, which again is first going to check to make sure we are actually initialized. So if we're not, then it's just going to return, and then it's going to call perif dinit, and it's going to do a full deinitialization, which is why it's going to pass the dinit full enum there. The reason why we have Deinit full and Deinit partial is because if we go to initialize the peripheral and something fails part way, then we want to partially deinitialize in order to leave the QuadSPI peripheral and the GPIOs and clocks and everything at the same state they were prior to us even trying to initialize, so that everything fails as gracefully as possible. So we only want to do a full deinitialization in a situation where everything has completely initialized successfully. We've used the driver for what we need to do, and then we don't need it anymore, so we can then deinitialize it. So by passing either Deinit full or Deinit partial allows us to select whether we're doing the full or partial deinitialization. And then setting our driver states to let it know that we're no longer initialized, and again that memory mapped mode would now be disabled. So we're going to have our perif init and perif deinit methods where the actual initialization and deinitialization occurs. Fix up our indents thanks to the copy and paste messing those up for us. Like so. All right, so our actual initialization of the peripheral and chip starts, of course, with setting up our GPIOs. Those guys are all getting set up in alternate function push-pull mode, and we're enabling a pull-up resistor for the chip select pin. There won't be any pull-up or pull-down used on the clock or data pins though. The particular speed that all the pins are going to be operating at is going to be set to high frequency, as we can see there. That's being used for all of the pins, and then setting the relevant GPIO ports, pins, and alternate functions for each of those as we've defined in the setup.hpp file. So it goes through and gets all 6 pins set up for us. And then we're going to go through and set up the actual QuadSPI peripheral. So first thing we need to do is enable a clock for that so that the peripheral has a clock to be able to operate. Fill out our structure to be able to define how the peripheral is going to be set up. So let it know we're using the QuadSPI peripheral, what our clock prescale is going to be, what our FIFO threshold is. We've also got to let it know things like how big the flash chip is, so that it knows not to try and access outside of the flash memory space, and a couple of other bits and pieces there, like how many cycles the chip select needs to stay high for, what clock mode we're using, what flash ID we're using. It is actually possible to use the QuadSPI peripheral with 2 flash chips hooked up to it. I've only got one on this particular Discovery board, but we can actually set up a couple of different ones and it can access both of those. It handles the particular chip selects and data lines as needed for a couple of them if it's set up that way, and letting it know that in this case we're not using 2 flash chips, so dual flash is disabled. And then just going through and getting that initialized. If that initialization fails, then we want to perform a partial deinitialization so that it goes through and turns off our clock, resets our GPIOs, things like that. Again, want to make sure it fails as gracefully as possible. We don't actually need the IRQs in order to get this driver working the way we're using it, but we've got those in there just in case we do need to enable those for a future project, just so that that's good to go. We can just uncomment that, and that's got the QuadSPI peripheral ready to go on the STM32 at that point. So the next stage of initialization is actually getting the flash chip ready to go. So the first steps that we want to do there is firstly to reset the chip, which we'll call one of our tool methods, so the imp reset method, reset memory method, to reset the chip. We're then going to enter QPI mode in order to get the mode of the flash chip working the way that we want it to be interfacing with the QuadSPI peripheral. We're going to enter 4-byte addressing mode so that we can supply 32-bit addresses to the flash chip effectively. Gives us a little bit more granularity with actually accessing the chip rather than 3-byte or 24-bit address mode. Need to let it know how many dummy cycles are required. So calling that, again, the tool method, dummy cycles config, and then configuring the output drive strength of the data lines on the flash chip so that they're set to the correct drive strength to match their connection to the QuadSPI peripheral. So for more information on this sort of stuff, it'd be worth having a bit of a read of the MX25L512 datasheet. It's a Maxim product, so you can just search for Maxim MX25L512 and it'll explain some of that stuff in a bit more detail. And then assuming we get to this point, then we've initialized correctly, so we can just go through it and return QA-OK. And again, for each of these particular stages of setting the chip up, if that fails, we go through and deinitialize everything so it fails gracefully and return a fail. Our deinitialization method is firstly going to check if we're doing a full deinitialization. If we are, then it's also going to go through and deinitialize the QuadSPI peripheral. Regardless of whether we're doing a full or partial deinitialization, it's going to turn off the clock to the peripheral, and it's going to go through and deinitialize all 6 of our GPIO pins. So that's how that all works there. Next methods we're going to take a look at are our actual tool methods, as those ones are fairly important and they'll give us a bit of an idea of how we use the QuadSPI peripheral and the HAL methods to actually communicate with the flash chip, because it's a little bit different than just using a standard SPI peripheral. So let's grab those guys and we're going to pop those in here. Again, we'll have to go through and fix up some of our indents. This code may look a little bit scary initially, but it does actually make quite a bit of sense when we start to go through what it's actually doing. So don't let it worry you too much. It's that one. This should be the last one. Yep, let's reset memory. Okay, so when accessing the flash via QuadSPI, there's 2 main HAL commands that we're going to use. 3 actually, but we're going to look at 2 first up. So the first is HAL QSPI command, where we're just sending a particular command, so one of the byte values that we defined at the start of this file to the flash chip. And to do that, we need to fill out the structure with the particular details about that command and how we want it to be sent and things like that as well. So, for example, we're using all 4 data lines to send this instruction, assuming that we are in a state where the chip is in QPI mode or where all 4 data lines are being used. So with that one, letting it know that we want to use that particular mode, we're letting it know what command we're sending, which is one of the defines that we put at the start of the file. So in this case, reset enable. Then letting it know we're not using an address, that there's no alternate bytes, there's no data being sent, how many dummy cycles to use, and we're also letting it know that we're not using DDR mode to communicate with the chip, because QuadSPI can actually do double data rate as well. And then just a matter of calling HAL QSPI commands, passing it a handle to our peripheral, a pointer to the actual command structure that we've filled out, letting it know what the timeout value is going to be, which we're just using the default HAL timeout value for that peripheral. So this is basically enabling us to reset the chip, and then we're sending another command using most of the same settings, except just changing the actual command that's being set to reset memory, and then we're sending that command as well. And again, because this one's being sent in QPI mode or with the 4 data lines, this one's going to be sent that way as well. In the case where the chip is not in QPI mode and is only in SPI mode with a single data line, then we're also sending that same reset enable via that mode as well, just in case, to cover both cases. So regardless of whether it's in 4 data line mode or single data line mode. And we can see here we're telling it that we're sending it in 1 line mode to make that happen. So a little bit more complex than doing a typical SPI peripheral on a normal SPI bus. Doing a bit of a delay for 1 second, just in case the flash memory's got to go through and do a chip erase or something like that. It's not going to erase every time it initializes. So if you've written data to it previously and then you've gone and reset the STM32, it's not just going to erase all the data on you. There's only certain situations where it may do that. Again, it's worth having a look at the data sheet about when it may or may not do that, but it is safe to write data to it and assume that that data is going to be there when you start the chip up or reset the chip again, with the exception of you actually telling it to do a full chip erase. Now, one of the other commands that we use with the HAL is this AutoPolling command. And what that does is basically tells it to keep checking with the chip until it reaches a particular state before it continues. So for example, we can use AutoPolling to check if the chip is busy, and as long as it continues to be busy, then it's going to stay in that AutoPolling function and only come out of it once it either times out or the chip stops being busy. So in the situation where we use the AutoPolling command, we use our command structure like we have for the previous commands, but we also use this configuration structure here as well, which is defined up here. So the QSPI AutoPolling type def. Now, this one allows us to define sort of what state we're getting the AutoPolling function to look for prior to it actually continuing. So we've got this match member of the structure. We've got a mask member of the structure, and we've got a match mode member. And these ones kind of explain to it how we want to check what's going on. So in this case, what it's going to be doing is it's going to be looking at the write in progress bit of the status register. And essentially, if that bit is set, so if it's a 1, then we know that the chip's currently busy writing to the chip, and we need to wait before we start sending it more commands. If the write in progress bit is not set, so if it's a 0, then we're good to go, and we can continue on and send it more commands. So what this is saying is that the mask it's using is the write in progress define that we've defined previously, which basically will apply the mask to it'll read from the status register, apply a mask to that byte to mask out only the bit we're looking at, so the write in progress bit in this case. And then it's going to see if it matches with the particular value that we're looking for. So in this case, we want that bit to not be set in order for it to continue. And we're telling it that we want to use AND as the match mode for that one. So effectively, that kind of tells it how to apply the mask. So it's going to AND the mask value with the value it receives from the status register. We're telling it how many bytes to actually use to do that match with the mask, which is 1 byte because the status register is a single byte value. And then we've got an interval value, which we don't really need to worry about. And then we've got an automatic stop value, which is basically when we enable automatic stop, then it knows that as soon as we meet the particular condition we want to meet, then it will stop polling the chip and allow us to continue on with the other steps we want to do. So in this case, we're sending it an instruction. We're in single data line mode at this point, so not quad data mode. Sending it the command to read the status register. So that will continue to be sent, and it will continue to read the status register up until the fact that the write in progress bit is not set, and telling it that the data mode is also single line. So effectively, the instructions can be sent in single, dual, or quad mode, and the data can be sent in single, dual, or quad mode as well, depending on how many data lines it wants to use. So we need to let it know we're using single line for the instruction and single line for the data. And then again, similar to our HAL QuadSPI command method or function, when we call HAL QuadSPI AutoPolling, we pass it the handle, we pass it a pointer to the command, and in this case, we also pass it a handle to the configuration, so what it's actually looking for when it's polling the chip. And then we also have our timeout value as well. So that's kind of how auto polling works. It's actually really quite useful, as we'll see moving forward. So the next thing that it needs to do when it resets the chip is read the status register, so that we have a copy of that status register to be able to use when we go to write back to the chip, which we'll see in a moment. So in this case, we're just sending a command as we did before, but we're also receiving some data as well. So in our command, we're telling it how much data, so a single byte that we're going to be reading. So that's sent as part of the command side of things. And then when we tell it to receive, it's automatically going to do just the number of bytes that we've specified when we've sent the command. We're then going to enable write operations. So writing to various parts of the chip is not enabled by default. We actually have to ask it to enable writing to the chip, which is what we're doing here. And then we're using our auto polling to check to make sure that when the chip actually goes into write enable mode, because that may take a little bit of time. So again, we're telling it that we want to mask out the write enable bit of the status register, and that we're looking for that bit to actually be set. So similar to how we were doing it before, except when we were dealing with the write in progress bit, that needs to not be set for us to continue. And again, letting it know that we want it to automatically stop when the condition we're looking for occurs. So that's basically just putting it into write enable mode, again using our auto polling command. And then finally, we're telling it that we want it in QuadSPI mode. So this is where we're using the data that we read from the status register. So we're ORing that data with the quad enable bit so that that bit is now set. And then we're writing that status register data back to the status register to tell it that we want it in QuadSPI mode, just like so. Actually, in this case, we're not writing to the... Oh no, we are writing to the status register. So although we can read from the status register and the configuration register independently, we use a single command to write to both of those in one go. So in this case, even though we're using the command to write to the status and configuration register, because the status register comes first and then the configuration register, when we tell it only to write 1 byte, it's only going to write that first byte, which is the status register. If we wrote 2 bytes, then we'd be writing to the status and the configuration register. So I hope that makes a little bit of sense, and then just delaying for 40 milliseconds to make sure that that has time to do what it needs. So that's how we go about resetting the chip. The next tool method we have is to put the chip into 4-byte addressing mode or 32-bit addressing mode. And that's a fairly simple one. We're just going to be sending the command to enter 4-byte address mode. Again, using similar command settings as before. Because we're writing to the chip, we need to make sure that it's in write enabled mode first. So we're using that tool method to make that happen. And then sending the command to put it into 4-byte addressing mode, and then using AutoPolling to make sure that when the flash chip has finished doing that, so we can continue, which is what our imp AutoPolling memready tool method does. It just checks to see if the chip's busy, and once the chip becomes ready or it times out, it will return. We've got the method to configure the number of dummy cycles. This one's basically just reading the byte from our status register, reading the byte from our config register, enabling write on the chip so that we can write data back to it, and then we're then going to be updating the configuration register data that we read with the new setting for our dummy cycles, and then we're going to be writing the data back to our status and configuration register, because again, we read those two separately, we write them together. So we'll notice we're writing 2 bytes here, which means it's going to write the first byte to our status register, the second one to our config register. And then, of course, just a bit of a delay there to make sure that it has time to complete. We've got a command to put the flash chip into QPI mode or quad data mode so that it's using all 4 data lines. Again, fairly simple. We're just sending the command to tell it to enter quad mode, and then we're polling to make sure that the chip has gone into that mode and that it's not busy. So in this case, when we set up our mask, we're telling it that we want to make sure that our quad N bit is set and that our write in progress bit is not set. So that's why we set up our mask and our match with those particular settings. We've got another one to exit QPI mode so that we can go from quad mode back to single mode if we want to do that. And that's as simple as just sending the single command for that one. We've got one for setting our output drive strength, and this one, again, just reading from our status register, reading from our config register, putting the chip into write enable mode, and then updating the status and config registers with the modified values in order for it to have the updated output drive strength that we're looking for. So it's just modifying that data there and then using the command and the transmit to write that data back. So again, reading the status and config register separately, but writing back to them using a single command, just because that's one of the quirks of the chip. And then we've got the tool method to put the chip in the write enable mode. So the first one sends the command to tell it that we want it in write enable mode, and then we're using our auto polling to wait for the chip to go into that mode. So just waiting to see that the write enable bit has been set in the status register. And then last tool method is our auto polling memready, which basically when we call that one, it's just going to sit there and check the status register until the write in progress bit is not set anymore, so that we know that the chip is not busy doing something and we're good to continue. So again, just using our auto polling command, and setting it up so that it's looking to make sure that write in progress bit is not set. So that's kind of, these are the most complicated parts of the driver, which is why we break those out into tool methods. Again, it saves a bit of code duplication in various other parts of the driver, and it means that when we go to do the initialization of the chip in here, we can just call those tool methods. It keeps the initialization code much neater, rather than having a huge initialization section, break all of those bits out into their own respective tool methods, especially because some of those tool methods we're going to need to use when we're doing other things to the chip. Like if we're writing data to it, we're going to need to be able to put it into write enabled mode. So instead of having to send the command and do the auto polling to make sure that it's in write enabled mode, we can just use the tool method for it. Saves code duplication and keeps things looking a little bit neater as well. So that's our tool methods. I hope that kind of makes a bit of sense and you get a bit of an understanding of how we go about using the HAL methods to actually communicate with the flash chip via our QuadSPI peripheral. And then we've got our other methods which we're going to add in. The first two being to enter and exit memory mapped mode, which will pop in here, fix up those indents there, and fix up these indents here. Now the strange thing is that the HAL has a command to put it into memory mapped mode. It doesn't have one to get it out of memory mapped mode, or I've not figured out the particular way to make that work, even through a bunch of experimentation previously. So when I go to enter memory mapped mode, we basically let it know what instruction it needs to use in order to be reading data from the chip. Because again, as I mentioned earlier, in memory mapped mode, we can only read, we can't write. So in order to do the read, it's going to need to know what command to send the flash chip to do the read, so that it takes care of that automatically whenever we go to read from the address space that matches where the flash chip is located. So we tell it what command to use, what settings to use for that command, and telling it that it's using 4 data lines for the data, 4 data lines for the address, and 4 data lines for the instructions, so that we're making use of parallelizing the data so we can get more data moving quicker. It's also got some timeout settings. So effectively, when it's in memory mapped mode, typically the chip select line is going to be held in a state where the chip is continuously selected, so that whenever it goes to access that, it's going to be able to try and access the data as quickly as it possibly can. We can set it so that if we haven't accessed the chip for a certain amount of time, that it can actually time out and disable chip select if we want it to. And the reason why we may want it to do that is in a situation where we're running the discovery board on batteries, for example, because the flash chip will be consuming more memory when chip select is enabled. So we can go through and do a timeout there with the settings here if we would like to. However, I typically run it off not on battery power for this particular board. So in this case, I basically just leave the timeout disabled so that chip select's always selected when we're in memory mapped mode. And then just calling the method to let it know to put the peripheral into memory mapped mode. And then of course, just tracking it inside the driver so that we know that memory mapped mode is enabled. Now, as I mentioned, the HAL method will allow us to put it into memory mapped mode. I've never been able to figure out how to get it to take it out of memory mapped mode. So my workaround for that is basically to go through and deinitialize the driver and reinitialize it. And by doing that, when we deinitialize the QuadSPI peripheral and we reinitialize it, it's going to be out of memory mapped mode by default. So acts as a bit of a workaround. Still going to work fine doing it that way. And because of the way we get the deinitialization method to work, so that it's deinitializing everything, so that it's at the same state it was before we initialized anything, that will work without causing any potential issues for us as well. So it's kind of a nice, easy workaround to make that happen for us. And then we have a bunch of methods to allow us to access data on the chip or to write data, do erasers, all of that sort of stuff that we saw before. Let's get those copied across and fix up our indents again. It'd be nice if it would copy and paste and keep my indents the way I want them, rather than having to make me fix them up each time, but that's okay. Where are we? It's that one. It's our erase methods, our write methods. And our read method. Okay. Let's fix these guys up as well. All right, so in order to read data from the chip, we need to supply it of the address that we want to read from. If we're not in memory mapped mode, then we can use these following methods. Then in that situation, the address that we provide to these methods starts at 0, which is the first byte of the flash chip, all the way up to our 64 megabytes. So we tell it what address we want to start reading from, give it a pointer to where it's going to put the data that it's read, and let it know how many bytes that we actually want to read from the flash chip. It's going to go through and send our command to read using 4-byte addressing mode. Again, it's going to do so using 4 lines for the instruction, 4 data lines for the address, and 4 data lines for the data itself in order to get best performance, make best use of the QuadSPI peripheral. It's going to go through and send the command to let it know that we want to read from the chip, and then it's going to go through and actually read the data as we want there. Now it's also manipulating our DCR register in here as well. I wouldn't stress too much about why it's doing that. You could have a look through the reference manual for the F769I and have a look at the DCR register. But essentially that just allows it to make sure that the read is occurring correctly. If you have any questions about that as well, feel free to ask them in the comments or on our subreddit. We've also got our read subsector and read sector methods, which allow us to just pass an index to say which subsector or which sector we want to read from, so that it reads a whole subsector or a whole sector, respectively, rather than having to provide the actual address. Now, what this will do is it's still going to use our normal imp read method that we just looked at, but it's going to figure out what address that subsector or sector is at, just by multiplying the index by the subsector size or the sector size, respectively, due to the fact that the flash chip typically works with an address rather than the index of a sector or subsector. So it just makes it a little bit easier if we're, say, when we're dealing with FATFS, we're going to be reading and writing in blocks of data. So typically we're going to be looking at reading or writing a particular size of block, and we can use the read sector or subsector or write sector or subsector methods to make that a tiny bit easier. So that's why those guys are in there. Most of the projects that I've worked on, because you need to be erasing the area of memory you're going to write to before you write to it, I'll typically break the data up that I'm going to be storing on the flash chip into like subsectors or sectors or whatever, so that when I go to write the data to it, it makes it much easier to do the erase, because we have methods to allow us to erase a particular sector or subsector before writing to it. Following our read methods, we've got our write method. This one's a little bit more complicated, simply because when we're writing to it, partly because of the way the chip functions, the chip has a buffer in it, like a RAM buffer basically, so that when we do a write, it's going to store the data temporarily in that buffer or cache almost. It's basically a cache. So it'll write the data to the cache, and then the chip's going to take care of taking the data from the cache and putting it into the respective area of flash memory. Now, the cache size is only 1 page in size, so 256 bytes. So when we go to write data to the chip, we need to do it in chunks of 256 bytes, which is why this is a little bit more complicated. So the particular instruction we're sending into it is to program a specific page with data. Again, doing everything using 4 data lines for our instruction, our address, and our data. And basically iterating through in this while loop and writing the required number of pages in order to write the complete amount of data that we want to put in there. So writing in the 256 byte blocks that we're looking for. So putting the chip in write enable mode first up, sending the command to tell it that we want to write data, transmitting the data to it, and then checking the chip using AutoPolling memready to wait for the chip to be ready and have completed that write before we try and write the next block of data to it. So it makes it a little bit more complicated, but that's kind of the way it needs to work for that particular chip. And this does actually work quite quickly, even though it's completing multiple steps per page that it's writing. I generally find, thanks to the use of QuadSPI, actually getting data written to the chip is not really, and unless you're writing, the whole 64 megabytes or huge chunks of data or something, you generally get pretty good performance out of it. We've also got the methods to be able to erase and write a single subsector or erase and write a single sector, which means that we can do the erase and the write in one step using the driver, rather than having to worry about doing those 2 separate steps when we write data. And this is basically just going to go through and erase the particular sector. It's calculating the particular address where that subsector is located, so that when it goes to do that write, it can actually pass that address to the write method, and then it will take care of actually writing the number of pages that needs to be written in order to write that into our subsector. Same thing with the sector. It's just we're dealing with 64 kilobytes for the sector, whereas we're writing 4 kilobytes for the subsector. And then we've got our erase methods. So this one's just basically telling it that we want to erase an entire subsector. So again, using the command similar to what we've done previously, putting the chip in the write enable mode, because basically to erase an area of memory, we're still kind of writing to that memory in order to erase it. Sending the command to make that happen, and then using AutoPolling memready to wait for the chip to complete that operation and be ready to go again. There is other ways that we could do this in order to make it more efficient, so that we can do other things while the chip is busy completing its task. But for most things, this tends to be quick enough in order to do what we need to do. So we may come back and look at further optimizing the driver to allow other stuff to happen while the chip's busy in future. But for the moment, we'll keep it a little bit simpler and go with this particular approach. Our erase sector address method is fairly similar to our erase subsector address method, except we're erasing a 64 kilobyte sector as opposed to a 4 kilobyte subsector. And basically identical except for the actual command that we're sending it, where we're telling it just to erase a sector rather than a subsector. We've got our other two methods where we can erase a subsector or a sector. These ones allow us to supply the index of the subsector or sector rather than an actual address. And much like we saw with some of our previous methods, it's basically just going through and calculating the address of that subsector or the sector respectively, and then calling the relevant method for that, due to the fact that what the chip wants is the actual address rather than a sector or subsector index. So again, just makes it a little bit easier if we're accessing the flash in chunks to be able to make that happen. And then our last erase method is to erase the entire chip. And again, fairly similar to what we're doing when we're erasing a sector or a subsector, with the exception that our instruction that we're sending is to do a bulk erase or to erase the entire chip. It write enables the chip, sends the command, and then waits for that to complete. So although this code might look a little scary when you first see it, it all kind of makes a bit of sense. Our final method for the driver is our getStatus method. And this one's also fairly simple. We're basically just going to be reading from the status register and checking to see if our write in progress bit is set so that we can tell whether or not the chip is busy. So we send the command, we receive that byte of data from the status register, we compare it with the write in progress bit. If it's 0, then we know it's ready to go. If it's not 0, then we know it's busy. So we're going to return busy or ready respectively. If we fail to do the send the command or receive the byte, then we know an error has occurred. So we return error in that situation. So that is all of those methods. There's a fair bit to the driver, a fair bit of code. We had 1,000 and something lines in the file, but this is probably the 4th or 5th generation of this actual code, which I've been using across a whole bunch of projects using these boards, and tends to work quite well. So we might go through and do a bit of a test with it, make sure that the drive is actually working correctly. So we're going to include our QuadSPI.hpp in here. And what we might do is just write some data to it, make sure that when we read the data back, it matches. And as long as it's doing that, we know that both the erasing, writing, and reading is all working correctly. We might have a bit more of a look at memory mapped mode in a future video, just so we're not trying to cram too much into this video. So where are we? Done our touch controller initialization there, so we'll do this after that. And go if QAD QuadSPI init. Don't need to pass anything to it. So if we get a non-zero value back, we know that that initialization has failed. And if it fails, we'll send a message out via serial, turn on our red user LED to let us know that there's an issue, and jump into an infinite loop so that we don't try and do something that with the peripheral or the chip in a state where it's not working correctly. So if it succeeds, so if we get a 0 or a QA-OK back from our initialization method, then we'll send out a message just saying that that has initialized. and we'll go through and run a bit of a test on the memory. So for this, we'll do a write to and a read from a subsector. So 4 kilobytes. It's enough to let us know that the QuadSPI is set up properly and it's communicating with the flash correctly. So we're just going to create a couple of arrays. We'll call this write data. And we'll make this 4096 bytes. And go through and put some data in our write data buffer, just so that we can compare the read data buffer and the write data buffer after we've done the write and read to make sure that that's worked correctly. So what we might do is we will make it so that it equals I and 0FF. So it's going to be incrementally writing values to it. So 0 through 255 8 times over the 4096 bytes. So that sort of gives us a pattern of data that's going to allow us to make sure that that's working correctly. For example, if you're reading from an area of flash memory that has been erased but data hasn't written successfully, then you would get all binary ones. So each byte would come back as FF in hex. So this just allows us to check that that's actually working correctly. And then we'll go QAD QuadSPI. It's not giving me the hints there, unfortunately, but that's fine because we can just do it this way. So we want to erase and write subsector, and we're going to go with subsector 0 and give it a pointer to the data, which will be write data, and then we're going to do the read. Going to read subsector 0 and pop that data into our read data buffer, and then I'll create a value to track whether or not it has passed the test or not, and then we'll iterate through all of that data. And if you write data at any one of the bytes doesn't match read data, then we'll set B passed to false. So after we've done this comparison, if B passed is still true, then we know that everything matches and we're all good. If it's false, we know it failed. So if B passed, actually we'll go if not B passed, then spell flash correctly might help. We'll go test failed, and we'll pop our user LED on. And jump into an infinite loop at that point because there's obviously an issue. But if we succeed, we'll pop out a message to let us know that that has actually succeeded. Let's see how many bugs we have today. Let's hold up on coffee while we're waiting for that to compile. Five errors, that's not actually too bad. Okay, just going to cheat and do a typecast on that so that it converts it to a uint8. Why is it not happy with that? What have I messed up there? Aha, we're accessing a singleton class. So we need to do it that way. That's better. Ah, might help if we provide it the array index, otherwise it's going to complain about that. That makes a bit more sense. Okay, no errors. Let's pull up our serial monitor. Get that connected to our chip. And let's dump the code over onto that. So it's just transferring the code for us now, resetting, and we have a failed test. All right. Why do we have a failed test? Let's get it to spit out the actual data that it has read back. Which way will we do this? Let's go 512 I++. Create a string that we can write some stuff into. I'm going to use sprintf, and then I'm going to write groups of 8 bytes in hex. So we'll go 0 to X, 2, 3, 4. Pop a thing in there to break them up, like so. Let's close. Oh, we'll just pop that one back over there, give us a bit more space. And then we're going to go, you write, create another value here. Just going to call that index, uindex equals I times 8, because we're doing them in groups of 8. So go u read data I uindex plus 1. Pop that on another line. Actually, the first one will be plus 0. 2, 3, another line, like so. 2, 3, 4, 5, 6 and 7, and we, rather than doing all of the bytes first up, let's just do 64 bytes, so 8 groups of 8. And we will urt link tx string cr and write that one out to serial. Now, I'm going to do this twice. We're going to do it for the data that's being written as well as the data that's being read, just so that we can sort of compare them visually as well, help us to spot any patterns with what's actually going wrong. So replace you read data with you write data for those ones. Excellent. What do we got going on there? Oh, semicolons. Always helps. Okay, pop that onto the chip, bring back our serial monitor so that we can see what's actually happening. That's not working properly. Might actually be writing too much data too quickly, which is why it has done that. So let's just put a short delay in there. We'll go with 10 milliseconds. Also write a blank line in between our write data buffer and our read data buffer as well. So just use txcr for that one to write a carriage return, and pop a delay in for this one as well. Might need to increase the delay if it still doesn't work properly, but I'm guessing that was just a buffer overflow that we're causing in our serial subsystem. Switch back over to our serial monitor and see what we get this time. All right. So what we can see straight away is our data looks good that we're writing. That buffer looks fine. However, if we look at our read data buffer, all of the bits are set, which tells me straight away that it is doing the erase correctly, but it's not writing the data correctly when we go to write it. So let's figure out why that may be the case. Let's pop that off the screen for the moment. And we're using read subsector for that one. Make sure that it is using the correct methods. So erase and write subsector is calling imp erase and write subsector, which is what we want. Jump over to here, let's find erase and write subsector. which all actually looks good. Right. All right, let's go and modify this slightly. Let's go erase subsector, tell it to erase 0, and then we're going to go right. Address will be 0 because we're writing to the first subsector. Pop in your write data and QD QuadSPI. Actually, we'll be doing 4096 bytes, so 4 kilobytes. Let's see if that works. Still not doing the write correctly. Okay, I'm going to take a quick bio break and then we're going to look at why that may be happening. So I will be back in a moment. And we are back. All right, everything looks like it's working there. So let's close that guy. We don't need that right now. What I'm going to do first up is pull up some code that I know has worked for this previously, where we've used this driver or a variation of it. Let's jump on here. We want our code library. Where is one that I know has worked correctly? Maybe this one? No. Maybe this one. Let's open that up. So we're just going to go through and check all of our basic stuff first, make sure we're definitely using the right GPIOs. Pop that on my other screen. Make sure all of that stuff's correct. It seems that the erase part is working correctly, or the chip has already been erased. So I want to make sure that we've got everything correct. With the pins and everything first up. So GPIO pin 6 for our chip select, correct. GPIO pin 2, port B for our clock is correct. C9, C10, E2 and D13 are all correct. I'm wondering, because one of the changes that I have made to this driver as opposed to the previous one is that I haven't enabled our interrupts, and I don't think that's going to have any impact, but it's always safe to double check. If you know something has changed from code that has previously worked to code that isn't working, check the obvious stuff first. Let's have a look at getting a priority in for that one. I want this to be named slightly differently. How have we named QAD IRQ priority previously? QAD IRQ priority flash. Go into here and we'll pop this into our priority list. Wasn't expecting a challenge this evening, but we got one, so let's make it work. Set it at a fairly low priority. Let's run that. I doubt that's going to fix our problem, but maybe it will. No, good. So let's not use those. And let's make sure we're setting up our peripheral correctly. Also may want to just double check that we're setting up our clocks correctly. I don't think there's anything specific that we need to do for QuadSPI. No. What clock is our QuadSPI peripheral using? Where's it getting its clock from by default? Again, I don't think that's the issue, but go through step by step, make sure that everything is making sense. Okay, clock config. in here somewhere we should see a mux for our QuadSPI clock if it has one. Y2C, USB, UART, low power timer, CEC, STM32. Not seeing one for QuadSPI, which means I don't believe it has a mux. Which is good because then we don't need to worry about that. I believe QuadSPI should be pulling its clock signal directly from the bus it's connected to, which looks correct. Awesome. Let's close that. Alright, that's going back to what we want. Clock prescale is 1, FIFO is 16, shifting on half cycle. The position value should be correct. There's 6 zeros in there, correct? Yes, there is. 4 cycles, clock mode 0, flash ID 1, dual flash disabled. And initializing as expected. And I'm doing reset memory, enter QPI, enter 4-byte address, dummy cycles config, and output drive strength config is correct. Now, where is our write? Because I believe that's where we're having an issue. MU page size we have set to 256. Yes. And if we double check here, that is the same. Wonderful. So issues not there. That all looks correct. Should actually in here be returning the value that we get back from, actually, does erase return a value? I believe it does. This might help us track down where the issue is. So if that doesn't equal 0, then return QA fail. And same with this one. If that doesn't equal 0, then we'll return QA fail on that one also. And we're going to do the same for this. Probably should have written it this way first up, but yep, that's that one, and there's also, no, these ones are returning correctly. About our reads, yep, reads are correct, so the only place we really messed that up is in erase and write. Now what we're going to do is we're going to check the return values on these. So if any of these fail, we'll send out a message letting us know. And this is where serial can come in really handy for debugging. Okay, let's pop that on there and see what we get from serial. Okay, so none of those gave us a message saying that they'd failed because we haven't got an erase write or read fail message coming up here. So next test is where we're going to, we don't want to close that yet. We want to reduce the amount of data that we're reading and writing. And we're going to swap this over to use our, again, simplify stuff as much as possible. So I'm going to read from address 0 into uread data, and let's do 10 bytes. Might help if my camera was working correctly. Let's change cameras. That'll do. Fix that one up a little bit. We've obviously gone over an hour for this video. Oh, nearly 2 hours. Okay, cool. It's going to be a long one. All right. Downloaded successfully. What did we get? Okay, so the 10 bytes that we read back are still all ones. The rest of it's garbage because that's just what was in RAM. The buffer hasn't been cleared prior to us doing anything with it. Just so that that doesn't go confusing us, let's go uread data I equals 0. So just flush that buffer prior to us actually using it. Pop that onto our device. It's turning into a bit of a long video, but I'd like to solve this prior to the end of the video. Okay, still getting all ones coming back. Which does make me think that our erase and our read are working correctly, but there's something wrong with the write. Curious. All right. Another situation. If the code all looks like it's correct, but the issue keeps occurring, let's grab hold of another discovery board and see if we still get the same error or if it's board specific. So we will just move the camera here. Going to disconnect our serial for the moment. Plug in another F769I Discovery board. So I've got one of the other boards that I have here for testing, which is this one, which has the joysticks and stuff connected to it. So we're going to dump the code on that one and see if we run into the same error. So we'll connect our serial back up. Find which port that one's on. It's on COM3. Let's go with that. Connect that. No. Why? Let's open a fresh copy of that. Yep, that's connected. Let's dump the code on there. This will allow us to see whether the issue is with the code or if it's with the hardware. If it fails this time, it's a code issue, which it probably is. Exactly. Okay, so we know it's not a hardware issue, which narrows it down further. See, I think this board has got data on it somewhere. Let's just try and read subsector 100 and see what data we get back. And we're going to just comment out our write for the moment and our erase. And let's just see what's on the chip. If this is the board I think it is, then there would have been a whole bunch of log data written to the flash chip last time it was used, which means that we may just see some data coming up. No. So the chip has definitely been erased. Or there's an issue in a place I'm not looking. Okay. Now I'm assuming that the old code that I'm referring to actually works. Maybe it doesn't. Let's see if we can find another bit that has a flash driver in it as well. Let's go back to the first time that I wrote the flash driver, where I know that it was definitely 100% working. However, that was written on a Mac, so I can't open it in QuadSPI, but we can open up the source files and stuff in Notepad++. That will be this one. When we were coding the drivers, and we have a flash driver. That'll be in there. There's a header file for that. It's that one. And a source file for that is that one. Okay, this is all C code rather than C++. We got B6, B2. Let's pop that on the other screen so we can compare it. Make sure, again, we'll start with our GPIOs and everything. B6, B2, C9. Haven't made a spelling mistake in here. No, they're all correct. We haven't made a spelling mistake in our peripheral initialization, hopefully. CS, clock. Data 0, data 1, data 2, and data 3, they're all correct. And all our pins match up. E2, D13. That's all correct. That is all correct. There's nothing additional that we're doing there. Okay, our code for our write this code has obviously been copied and pasted across the various generations of me using this driver because it's pretty close. In fact, let's do it this way. That's all the same. Now our read. All looks correct. It's turning into a bit of a weird one. One of the differences in this driver is that I actually go through and do a test on the flash as part of the initialization stage to make sure it's working. So it writes a page of data and reads it back, which is 256 bytes. And unfortunately, because of... No, I don't want to update. Because of the way things are connected on the board, I can't just chuck the oscilloscope on it, which would be one thing that I'd like to do just to double check. And seems to me the issue's not in the driver unless I'm missing something that's staring me right in the face. All right. Now, I'm assuming that we're getting all ones back because we're reading erased flash. That may not be the case. Although, if there was something wrong with the data lines and they were stuck on binary ones, we'd be receiving QA fails at the points where it's going to check the status register, because the write in progress bit would be showing as being set if the data lines were all high continuously. So I don't think it's that either. Nothing in the system initialization that I think is incorrect. I believe it's initializing correctly. It's definitely telling us it's initialized correctly. Now, we do have a bit of a different issue, which is buffer overflow happening in here, which is why we're getting a few of these things on the same. No, it's not actually buffer overflow. I'm just not telling it to put in carriage returns. Let's fix that. That'll at least get that little issue out of the road. Give myself another 20 minutes. If I haven't found it, we're going to be doing a part 2 on this one, because it's 2 hours and 10 minutes worth of video so far. Okay. Let's have a look at this again. The only thing that's really changed is me not enabling IRQs. That I can think of off the top of my head from code that was previously working. However, I haven't put in IRQ handlers there. Let's just enable that just to get that out of the road. Pretty sure that's not it. We tried that already. But let's try it again. Now. Right. Let's grasp at some straws, why don't we? So modify this so it acts a little bit more like the code that we were just looking at in Notepad++. And what have we got? Same result. Going to kick myself if it's something simple, which it probably is. Where's our... No, so they're all definitely calling the correct methods. Right. All right. Have an idea. Let's take some code that works. Or I assume it works. Pretty sure it did last time we used this, so I'll get it to jump into an infinite loop there, because we don't want it to do anything beyond that. We're going to create a 256 byte buffer. And what's the methods in here called? To address 0 and size is 256. Let's put some data in there. And let's use this code to write data to it. which it should do correctly. Haven't compiled this code in well over a year, so let's assume that it's going to work correctly. "30 warnings." That's because I verified. Just reset. Awesome. Now we're going to use this code to try and read the flash and see if we get data. So we're not going to erase it in here. We're not going to write anything to it. We just want to read 256 bytes and see what we get. I have a feeling this video could end up with a part 2. Again, we're reading all ones. That's no, not that one. That one. Actually, let's just go. There's the test that I'm doing in. Oh no, that was in the other code we're looking at. There's that. That's in there. Double check what addresses we're using there. It's all zeros. So that is fine with the addresses being zeros there. I'm going to create a string and I'm going to do something similar than what we did previously, where we're just going to write out the first 8 hex values, first 8 bytes. Four, 0, 1, 2, and 3. So it'll give us the first 8 bytes, and we should get value 0 through 8 because that's what we're writing to it. What's the erase method there? Let's try that and see what we get. Might help if we actually tell it to print that to serial. Otherwise, we're going to get nothing being printed out. That might work a bit better. Hoping people are finding that this is entertaining, watching me try to debug this, because it wasn't what was planned for the video at all. But, you know, shit happens, as they say. How about that? It works. Kidding me. I wonder. Where are these declared? They're declared in the CPP. Are the commands correct? 66 and 99 for reset enable and reset memory. Not read status register. Where's our register commands? Register commands, read status register 05, 15 and 01. Those are correct. 4-byte address mode. Enter 4-byte address mode is B7. Those are commands for quad mode. It's 35 and F5. Those are correct. Read operation commands. So read commands. Read 4-byte address command is 13. Write enable. Where is our write enable on this one? Write enable is 6. Right. Program operations. Page program 4-byte address is 12. Subsector erase is 21. Sector erase is DC. Okay, but which are those actually using in those particular bits? QuadSPI read 4-byte address command. It's EC. Wait, what? No way. You're kidding me. You are kidding me. Okay. It's definitely what that's using in that code. QuadSPI page program 4-byte address. That's 12. That's EC. I believe we have just found the bug with 3.5 minutes to spare before I was going to look at another option. Looks like we may have been sending the wrong data, the wrong command. Gonna be super happy if that was it. Let's do that. Let's see if persistence has won us the working code. And that is what I love to see. This is why I love doing this, guys. Alright, if any of you are actually still watching 2.5 hours into this video, this is why I do this. Because the sense of winning just from kicking its ass right now is phenomenal. Right. Let's use the methods we actually wanted to be using. Delete that. Delete that. I don't even care about checking return values at the moment. It's just erase and write to subsector 0 and read back from subsector 0. And let's see what we get. All the rest of that's fine. We're just going to do 8 groups of 8. Yes, I do want you to save it. Thank you. Pop it on there. Let's see if we win. And we win. We have a working driver. All because one byte was incorrect because I screwed something up when I copied code over and modified it for QuadSPI. So there we go. Should have had that like an hour ago. But anyway, that is working and I am super happy about that. Perfect example of if you've got a bug and you can't see it and you've double checked something a bunch of times, the bug is not where you're looking. And it's a trick I tell myself regularly, but sometimes you don't know where to look. So that makes me very happy. If anyone is still watching at this point, I really do hope you found it entertaining. I hope maybe you've learnt something from the particular debugging process and how to actually narrow down where the bug is. A lot of those techniques are the same techniques I use anytime I get a bug like that, and thankfully that was a little bit of an interesting one. So again, thank you to all of the awesome people that watch my videos, that like and subscribe. If you did like this, love it if you hit a like. Love it if you subscribe if you haven't already. And if you do want to help the channel out, we do have a Patreon. That one doesn't work. That one works. But thank you to Craig and Luther, who are our 2 patrons at the moment that are helping to move the channel forward. Apologies about this camera. The other one that works for about an hour or so and then it decides to misbehave. And we're well beyond an hour at this point. Feel free to jump on our subreddit. We have a GitHub where this working code will be going if you want to get access to that. And in the next video on this series, we will be looking at a working SD card driver. So wonderful. Didn't even have to do a part 2 on this one. I am super happy. Who knows? I might even have some more coffee, even though it's 1:15 midnight, and do a 3rd video in a row, because this is the 2nd one I'm recording. Yeah, so why not? Gonna go and have a bit of a breather, maybe take a bit of a walk, and write some more code, I think. So again, thank you for watching. Don't forget to like and subscribe. Hope you're having a wonderful day or evening, morning, night, whatever it is where you are in your part of the world. And thanks for watching.